All right, I'm continuing looking at polynomials and the behavior of polynomials, and I'm specifically going to look at the extended discovery exercise number 1 on page 291 in section 2. And what we have going on here is we have Torticelli's law, which talks about how quickly amount of a substance will drain from a tank. So let me write in this law for this particular tank, and we'll talk about what's happening. And I hope we can see some things happening here coming out of it. So one of the first things that we would like to look at this is this, and I'll read the full question here. A cylindrical tank contains 500 gallons of water. And notice how that 500 shows up in the function for us. A plug is pulled from the bottom of the tank, and it takes 10 minutes to drain the tank. And so this term here is the 10 minutes to drain, because when this is 0, when the time is 0, this is 1, and all 500 gallons are still there, right? So we could look at this. If I said A of 0 at the starting point, I would have 500 times 1 minus 0 over 10 squared, which is 500 times 1 squared, or 500. So this function at the beginning has all of the gallons still in the tank. But it says in 10 minutes, the tank will be drained. So if I look at 10 minutes, I have my 500 gallons times 1 minus 10 over 10 squared. Well, 10 over 10 is 1, and 1 minus 1 is 0. And so 0. And so this function works from beginning, showing us everything in the tank when the time is 0, till the end when time is 10, that there's nothing in the tank. And so this is really what the first question wants to ask. It says, what's a good domain for the function? And the domain for this function works out really nicely to be, it starts at 0 and ends at 10, because those are the limits that were put into it. The second part of this question says, okay, well, a minute into this, how much water is left in the tank? And so what we get here is we get 1 minus 1 over 10 squared, or 500 times 9/10 squared. And at this point, we could drop to our calculator if need be. That's 81 over 100. Right, 9 squared is 81, and if I divide that, that's 5 times 81, or 405 gallons. And then it goes, well, what is the degree of the leading coefficient? Well, if we look at this really, really closely, this is very, very similar to things we'd seen before. In fact, if I rewrite this, and were to multiply all of this back out, this would square just like a parabola. And so this would be t squared. And so the highest degree we can get is 2. And so this is a degree 2 polynomial. And what we want to figure out is, hey, has half of the water drained after 5 minutes? And if we look at this squaring term is probably going to tell us something that happens. But what we can actually look at is, okay, if half of the water is going to be 250 gallons. So I can look at exactly how much is at the 5-minute mark. And so that's 1 minus 1/2 squared, or 500 times, let's see, 1 minus 1/2 is 1/2, and 1/2 squared is 1/4, right? 500 times 1/4. And so 1/4, let's see, 4 for every 100, there'd be 200 left. No, that's not right. Let's see, 1/4 means that I have 25 for every 100, and 5 times 25 is 125 gallons would be left. My apologies for doing a quick fraction there. Trying to look where my calculator was and wouldn't see it, but right, 25 for every 100 and a quarter, there's 500, so there's 125 gallons left. And this is much less than a half. And so there would not be more than half of the tank left in half the time. So Torticelli's law says, hey, look, this stuff's draining. If we want to look at everything that's happening, the entire time is 10 minutes. Well, at the halfway point, more than half of the stuff is drained. And so it drains more quickly when there is more stuff in the tank. And this function kind of shows us that if we look at what is happening to it. And the book uses this as a good example of the other part of the title of this class, which is modeling, where we can have these things model across. If you ever have like a jug of water and you poke a hole in the bottom, it will shoot very far and quickly because the height of the water has more pressure. And as the water goes down, there's less pressure from the height of the water and it slows down. And this function is showing that. This function is doing this. This is a good model for that physical system.